of mass. In the topics we have done earlier, we have considered objects to be of point sized. A point sized particle doesn't have any spatial extension, while a non-point sized particle or object has some spatial extension in the space. Such objects can be considered to be comprising of infinitely small particles, each of which can be considered to be of point sized. A body which is a system of large number of such point sized particles is said to be rigid if it does not undergo any change in its shape or size under the influence of external forces. One can also say the relative positions of the particles of the body remains same under the influence of external forces. Let us consider 2 points A and B in a body with position vectors r1 and r2 at any time respectively. The body is said to be rigid if the separation between A and B remains unchanged with time. One can also say the position of point A with respect to point B will remain unchanged with time. Then we can define RBA vector, which is position vector of B with respect to A, which can be written as position vector of A, which is R1, minus position vector of B, which is R2. That will come out to be a constant with time. One can say it with respect to point A also. Therefore, ideally a rigid body is a body with a perfectly definite and unchanging shape. The distance between the points of the particles of such a body do not change with time and under the influence of external force. It is evident from this definition of a rigid body that no real body is actually rigid, since real bodies actually undergo deformation under the influence of external forces. But in many situations the deformations are negligible. In many examples involving bodies like wheels, tops, steel beams and planets, we can ignore they warp, they bend or they even vibrate. We can consider them to be rigid under all circumstances. Daily life objects in our surroundings can be complicated and ideal rigid bodies are hypothetical. While discussing the motion of non-point size object, here we will consider them to be rigid. Then what kind of motion can a rigid body have? The motion of a rigid body can be described as extending the description of motion of point size particles comprising the given body. The motion of point size particle have been discussed at length in the previous units of motion in the straight line and motion in a plane. Let us try to explore this question by taking some example. For example, first we take up translational motion. We consider a rectangular block which is sliding down an inclined plane without any sideways movement. We have done such problems in laws of motion. The block is a rigid body. Its motion down the plane as shown in the figure is such that all the particles P1, P2 and rest of the other particles are all moving together. That is, they all have same velocity at any instant of time. The rigid body here is said to be in pure translational motion. In pure translation motion at any instant of time, all particles of the body have the same velocity, and if any straight line inside a body keeps the same direction during the movement, all the particles forming the body move along parallel paths. If these paths are straight lines, the motions are said to be rectilinear translation. While if the paths are curved lines, the motion is a curvilinear motion as shown in another figure. Second motion we will take is a rotational motion. A rigid body is said to have rotational motion of about a fixed axis when the particles forming the rigid body move in parallel planes along the circles centered on the same fixed axis. If this axis, which is called the axis of rotation, intersect the rigid body, the particles located on this axis have zero velocity and zero acceleration. If you look around, you will come across many examples of rotation about an axis. For example, a ceiling fan, a potter's wheel, a giant wheel in a fair, and a merry-go-round, and so on. The figure shows here the rotational motion of a rigid body about a fixed axis. Here the axis is taken to be z-axis. You may notice that in rotation of a rigid body about a fixed axis, every particle of the body moves in a circle which lies in a plane perpendicular to the axis of the body and has its center on the axis. Let P1 be the particle we are considering arbitrarily chosen at a distance r1 from the fixed axis. Then the particle P1 describes a circle of radius r1 with its center at C1 on the fixed axis. The circle lies in a plane perpendicular to the fixed axis. The figure also shows another particle P2 where P2 is at a distance r2 from the fixed axis and it moves in a circular path of radius r2 with center at C2. The circle 2 lies in a plane perpendicular to the axis of the body. Note that the circle described by P1 and P2 may lie in different planes, but these planes however are perpendicular to the fixed axis. For any particle on the axis like P3, for which the distance from the axis is 0, all such particles lying on the axis of rotation remain stationary while the body rotates. This is expected since the axis is fixed. In some examples of rotation, however, the axis may not be fixed. A prominent example of such a kind of motion is a top spinning in a place. Here we assume the top does not slip from one place to another, so it does not have translational motion. We know from experience that the axis of such a spinning top moves around the vertical through its point of contact with the ground, sweeping out a cone as shown in the figure. This movement of the axis of the top around the vertical is termed precession. Also, the point of contact O of the top with ground is considered to be fixed here. The axis of rotation of the top at any instant passes through this point of contact O. Another simple example of this kind of motion is the oscillating table fan or a pedestal fan. You may have considered that the axis of rotation of such a fan has an oscillating or sideways movement in a horizontal plane about the vertical through the point at which the axis is pivoted, which is shown by the point O in the figure. While the fan rotates and its axis moves sideways, the point O remains fixed. Thus, in more general cases of rotation, such as a rotation of top or a pedestal fan, one point and not one line of the rigid body is fixed. In this case, the axis is not fixed, though it always passes through the fixed point. Now, we will talk about general plane motion. The rolling motion of a cylinder or a wheel is very common motion which is seen by us in daily life. If one watches different point of the motion, which is very peculiar in the sense that every particle seems to be rotating and moving forward simultaneously. In fact, it is a combination of rotation about a fixed axis and a translation as shown in the figure. If one considers or observes a radial line, it moves from point A1 B1 to A2B2. The motion can be seen translational or rotational simultaneously for this particular radial line. Any plane motion which is neither translation or rotation is referred as general plane motion. Plane motion is that in which all the particles of the body move in parallel planes. Pure translational and rotational motion can be considered to be special cases of general plane motion. We can say that the most important observation which can be concluded from the above motion is that when a rigid body is in motion or is not pivoted or fixed in some way is either a pure translation or a combination of translation and rotation, which is said to be plane motion. The motion of a rigid body which is pivoted or fixed in same way or some way is rotation. The rotation may be about an axis that is fixed, for example for a ceiling fan, or moving axis which is for an oscillating table fan. We shall in this unit consider rotational motion about fixed axis only unless stated otherwise. Now we will talk about another important criteria or aspect of rigid bodies, that is center of mass. The above discussion regarding motion of any rigid body motion, following points come up regarding the trajectory of different particles of body. First, in case of pure rotational motion, the trajectory of particle is circular. Second, in case of pure translational motion, trajectory of particles is linear, while in other cases the trajectory of different particles can be a bit complicated as the particles have both translational and rotational motion. Consider a rod thrown in air with certain velocity and try to visualize the trajectory of one of its ends. The following video might help in visualizing the trajectory of the end point of the rod. We have seen in projectiles the path of an object under the influence of Earth's gravitational force. It's a parabola, but that was when the object was considered to be a single particle or a point-sized object. The path traced by a point on the end of the rod shown in the film clip certainly is not a parabola. In fact, the rod is rotating as it travels further. So there is a centripetal acceleration as well as the vertical acceleration, which is the acceleration due to gravity. If one observes the point depicted as white dot, it moves in a straight line. The motion of any other point is not straight line. In fact, one watches carefully, it moves in a circle and simultaneously move in a straight line also. Can such a point for a system be identified mathematically? Let's try to do it for a simple system comprising of 2 point masses of different values separated but connected by a massless and rigid rod. If a single force is applied at a point on the rod closer to the lighter mass, shown in the figure by a small sphere, the system will move forward and simultaneously rotate clockwise. But when the same single force is applied at a point on the rod very close to the heavier mass, which is shown as a bigger sphere in the figure, the system will move forward and simultaneously rotate counterclockwise. One can explore by applying force at different points on the rod, then at a particular point called center of mass or denoted as Cm in the figure, the system moves in a direction of the force without rotating, or it shows only pure translational motion. The center of mass of the system therefore can be defined as it is located somewhere on the line joining the two particles and is closer to the particle having the larger mass. Hence, one can define center of mass as the point where if any external force acts, the system shows pure translational motion. We will now try to find out mathematically the center of mass of a two-point particle system. Consider a system of two particles of masses m1 and m2 having position vectors r1 and r2 at any time which is shown in the figure. Let net force acting on the particle m1 be F1, then F1 can be written as force F12 and F1 external, where F12 is the force on m1 due to m2 and F1 external is the external force acting on m1. Similarly, net force acting on particle m2 can be written as F2, which is sum of F21 and F2 external forces, where F21 force is on m2 due to the mass m1 and F2 external is the external force on mass m2. Using Newton's second law, m1 into a1 can be written as F1, which is the net force on particle m1 mass, which can be equal to be F12 plus F1 external. This gives us equation number 1. Similarly, m2 into a2 is equal to F2 vector, which is also equal to F21 vector plus F2 external vector. This gives us equation number 2. Adding the above two equation 1 and 2, we get m1a1 plus m2a2 is equal to F12 vector plus F1 external vector plus F21 vector and F2 external vector. As we know, F21 vector is equal and opposite of minus F12 vector as they are internal forces. Therefore, m1a1 plus m2a2 will give us F external. This will be our equation number 3. Here the external force is written as F1 external and F2 external, which are the sum of the external forces acting on masses 1 and 2. By definition of center of mass as the point where an external force acts on the system and it shows pure translational motion, hence it can be taken as the representative of the given system for describing the translational motion. Therefore, F external can be written as m1 plus m2 within the brackets with multiplication with ACM, which can be written as or can be expressed as acceleration of center of mass. Let this be equation number 4. Using equation 3 and 4, one can write m1 m2 within brackets ACM will be equal to m1a1 plus m2a2. Or we can write the acceleration of the center of mass as m1a1 plus m2a2 the whole divided by m1 plus m2. This is the equation number 5a. We can write acceleration as derivative of velocity. Therefore, the left hand side can be written as derivative of velocity of center of mass. The right hand side can be written as m1 into derivative of velocity of mass m1, which is dv1 by dt. Similarly, we can write for the second term. So, we can write the right hand side as m1 dv1 by dt plus m2 dv2 by dt, the whole divided by m1 plus m2. We can take the d by dt on the right hand side common and we can write dvcm by dt as d by dt of m1 v1 plus m2 v2 upon m1 plus m2. Therefore, one can also write the expression for velocity of center of mass as Vcm is equal to m1 v1 plus m2 v2 upon m1 plus m2. Let this be equation number 5b. Similarly, we can write velocity as derivative of position vector. So, the left hand side it becomes derivative of position vector of center of mass, and the right hand side we can write m1 dr1 by dt plus m2 dr2 by dt whole divided by m1 plus m2. We can write drcm by dt is equal to d by dt of m1 r1 plus m2 r2 upon m1 plus m2. Therefore, the location of position vector of center of mass can be given as rcm is equal to m1 r1 plus M2R2 upon M1 plus M2. This gives us equation number 5C. If the position vector of the point particles are written in terms of position coordinates, then one can deduce the expression for the position coordinates of the center of mass of the system. Let us say R1 vector is x1 I cap, y1 j cap, z1 k cap, where x1, y1 and z1 are the position coordinate of mass m1. Similarly, we can write R2 vector as x2 I cap plus y2 j cap plus z2 k cap. Let the position vector for the center of mass be RCM is equal to xCM I cap plus yCM j cap plus zCM k cap. Using equation 5, we can write RCM is equal to m1 multiplied by the position vector of m1, which is x1 I cap plus y1 j cap plus z1 k cap, plus m2 x2 I cap plus y2 j cap plus z2 k cap, whole divided by m1 plus m2. The position coordinates of the center of mass then can be written as xCM is equal to m1 x1 plus m2 x2 upon m1 plus m2. This is obtained after equating the x and the y components. Similarly, the y component becomes yCM is equal to m1 y1 and plus m2 y2 upon m1 plus m2, and the z coordinate for center of mass will become m1 z1 plus m2 z2 upon m1 plus m2. The expression which we have deduced here can be extended to find the center of mass of n point particle system, which can be written with the help of equation number 5a as xCM is equal to summation I goes from 1 to n mixi divided by summation I goes from 1 to n mi, where mi is the mass of ith particle and xi is the x position of the mith particle. Similarly, we can write yCM is equal to summation I goes from 1 to n miyi divided by summation I goes from 1 to n mi. The z coordinate can be written as zCM is equal to summation I goes from 1 to n mizi divided by summation I goes from 1 to n mi. The position of center of mass, if one carefully observes the above expression, is a weighted average in which each coordinate is weighted by the mass located at those points. The above expression for the velocity, which is the equation 5b of the center of mass, can be extended to n particle system in the similar way. VCM can be written as summation I goes from 1 to n mi vi divided by summation I goes from 1 to n mi. The above expression for the acceleration using equation 5c of the center of mass can be extended to n particle system again as ACM is equal to summation I goes from 1 to n miai divided by summation I goes from 1 to n mi. Now we will do some problems to understand or to apply the expressions which we have deduced. Problem 1. Find the center of mass of 3 particles which are placed at the vertices of an equilateral triangle. The masses of the particles are 100 gram, 150 gram and 200 gram respectively. Each side of an equilateral triangle is 0.5 meter long and the figure is given to us. If you see the figure carefully, with x and y axis chosen in the figure, the coordinates of point O, A and B, which form the equilateral triangle, are respectively 0, 0, 0.5 meter, 0 and 0.25 meter, 0.25 into root 3 meter respectively. Let the masses 100 gram, 150 gram and 200 grams be located at O, A and B respectively. Then the position coordinates of center of mass can be written as, the x coordinate can be written first as xCM is equal to m1 x1 plus m2 x2 plus m3 x3 whole divided by sum of m1, m2 and m3, which gives us 100 into 0 plus 150 into 0.5 plus 200 into 0.25 whole divided by 100 plus 150 plus 200. This on simplification gives us xcm is equal to 5 upon 18 meter. Similarly, we can do it for y coordinate for the center of mass. Ycm can be written as m1 y1 plus m2 y2 plus m3 y3 divided by sum of m1, m2 and m3. Therefore, Ycm becomes 100 into 0 plus 150 into 0 plus 200 into 0.25 into root 3 whole divided by sum of 100, 150 and 200. Ycm can be simplified and we get 1 upon 3 root 3 meter. Therefore, the position coordinates of given system for center of mass can be written as 5 upon 18 meter, comma 1 upon 3 root 3 meter. Center of mass of a system with continuous distribution of mass. We now know how to find center of mass for a system which has discrete n point size particles, but a rigid body like meter scale, flywheel, they are system of closely packed particles. Using equation 6a, 6b and 6c, therefore applicable to rigid body, the number of particles here, atoms or molecules in such a body is so large that it is impossible to carry out the summation over individual particles. Since the spacing of particles is so small, we can treat the body as a continuous distribution of mass. Consider a body having continuous distribution of mass. Let dm be the mass of an infinitely small element whose position coordinates are given as x, y, z. The elements can be considered to be point size. The summation over whole body can be replaced by the integral. If the mass of the given body is, let us say, capital M, then the equation 6a, 6b and 6c can be rewritten in terms of the integral. The x coordinate of the center of mass can be written as 1 upon capital M, which is the total mass, integral x dm. Remember, the integral is done over the mass of the element. Similarly, we can write y coordinate of the center of mass as 1 upon m, which is the mass of the body, integral y dm. And the z coordinate center of mass similarly can be written as 1 upon capital M, integral z dm. Often we have to calculate the center of mass of homogeneous bodies of regular shapes like rings, discs, spheres, rods. By using symmetry consideration, we can easily show that the center of mass of these bodies lies at their geometric centers. For example, for an object ring, the position of center of mass is at its geometrical center. For hollow sphere, again the center of mass is at the center. For solid sphere, again the center of mass is at the geometrical center of the sphere. Similarly, we can have a cylinder, the geometrical center is going to be at the half of the height of the cylinder, then center of mass will lie at that point. For circular disc, again the center of mass is at the center of the disc. For rod, it is at again the center of the rod. For a plane lamina, which can be either rectangular or square, it is at the intersection of the diagonals. While if the lamina is triangular in shape, the center of mass is at the point of intersection of the medians, which is also called centroid. But if you have a three-dimensional object which is rectangular or a cubical block, then the center of mass is at the intersection of the diagonals. Let us do a problem based on center of mass of a body which has a uniform distribution of mass. Find the center of mass of a uniform L-shaped lamina which is thin flat plate with dimension as shown in the figure, and the sheet is obtained by cutting 1/4 part of a square shaped lamina. Consider the mass of the L-shaped lamina to be 3 kg. Solution: choosing the x and y axis along the length and breadth of the given L-shaped lamina as shown in the figure, then we can have the coordinates of the vertices of the L-shaped lamina in the figure. We can also think of L-shaped to consist of actually 3 squares each of length 1 meter. The mass of each square is then 1 kg by the symmetry. The centers of masses for each squares will be at C1, C2 and C3. They are geometric centers and they have the coordinates half comma half meter, 3 by 2 comma half meter and 1 by 2 comma 3 by 2 meter respectively. We take the masses of the squares to be concentrated at these points. The center of mass of the whole L-shaped object, which is the lamina here, can be then written as xcm is equal to m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2 plus m3. x1, x2, x3 are actually the x coordinate of the center of masses of the smaller squares which we are considering. Therefore, we can write 1 into half plus 1 into 3 by 2 plus 1 into 1 by 2 whole divided by the total mass of the L-shaped lamina, which is 3. xcm therefore comes out to be 5 by 6 meter. Similarly, we can find out ycm as m1 y1 plus m2 y2 plus m3 y3 divided by m1, m2 and m3, where y1, y2, y3 are the y coordinates of the center of mass of the each square we are talking about. Therefore, ycm is equal to 1 into half plus 1 into half plus 1 into 3 by 2 whole divided by 3 kg. It comes out to be 5 by 6 meter. Hence, we can conclude the coordinate of the center of mass of the L-shaped lamina is 5 by 6, 5 by 6 meter. Alternatively, we know the expression for the position of center of mass is actually a weighted average in which each coordinate is weighted by the mass located at that point. Hence, the above problem can be done in a different way also. Let us consider the whole sheet of lamina to be intact, that is before a part is cut from it. The center of mass of the intact lamina will be at its center, that is at point D, which is shown in the figure. The coordinates for point D will be 1, 1 meter. The mass of whole sheet of lamina in that case will be 4 kg. When we consider the whole sheet, then it does have the contribution of the part removed also. So, if that part is removed as shown by the shaded part in the figure, then its contribution has to be removed when we want to find out the center of mass of the L-shaped lamina. The center of mass of the removed part is at the center of that small square, which is given by point G with coordinates 3 by 2, 3 by 2 meter. The expression for the center of mass when a part of a body is removed can be written as RCM is equal to M1 R1 minus M2 R2 divided by M1 minus M2. Here R1 is the position vector of the whole body when considered, while R2 is the position vector of the center of mass of the part of the body which has been removed. The x and y coordinates can be written as xcm is equal to m1 x1 minus m2 x2 divided by m1 minus m2. ycm is equal to m1 y1 minus m2 y2 divided by m1 minus m2. Here in this particular problem, m1 is the mass of the whole body, m2 is the mass of the part of the body which is removed, r1 is the position vector of the center of mass of the whole body, and r2 is the position vector of the center of mass of the body which has been removed. In the given figure, the given problem, we have m1 equal to 4 kg and m2 is equal to 2 kg. Position vector of the center of mass of the whole body becomes x1 is equal to 1 meter, y1 is equal to 1 meter. Position coordinate of the center of mass of the part of body removed are x2 is equal to 3 by 2 meter and y2 is equal to 3 by 2 meter. Therefore, x coordinate of the center of mass of L-shaped sheet of lamina can be written as xcm is equal to 4 into 1 minus 1 into 3 by 2 whole divided by 4 minus 1, which brings us xcm is equal to 5 by 6 meter. The y coordinate of the center of mass of L-shaped sheet or lamina can be written as 4 into 1 minus 1 into 3 by 2 divided by 4 minus 1 is equal to 5 by 6 meter. Now we can summarize what we have learned today. Center of mass of a system of particle or distribution of mass depends on the geometrical shape and the distribution of the mass of the body. Next, the position vector of the center of mass of a two particle system can be written as RCM is equal to m1 r1 plus m2 r2 upon m1 plus m2. The expression for position coordinates for the center of mass of the system which has n particles can be written as xcm is equal to summation I goes from 1 to n mi xi divided by summation I goes from 1 to n mi. Similarly, ycm can be written as summation I goes from 1 to n mi yi divided by summation I goes from 1 to n mi. The z coordinate for the center of mass for such a system can be written as summation I goes from 1 to n mi zi divided by summation I goes from 1 to n mi. While for a body of continuous distribution of mass, the expression for the coordinates can be written in terms of xcm is equal to 1 upon m integral x dm, ycm can be written as 1 upon m integral y dm, and zcm can be written as 1 upon m integral zdm. Often we have to calculate the center of mass of homogeneous bodies of regular shapes like rings, discs, spheres, rods. In that case, we use symmetry and we can easily show that the center of mass of such bodies lie at their geometrical centers. Thank you.